Howdy everyone. So I wanted to devote the next couple of minutes, maybe 2-3 minutes, to the topic of nonlinear least squares. So we discussed the least squares estimator, and we've seen that it's following a linear model where H is a matrix, theta is the vector of parameters we want to estimate, and there is some error here that I call n or noise. Okay, now let's assume that our model is nonlinear. So we have a function, a vector valued function f, and it received the theta as an argument, and also we have an error here. Okay? How can we solve that? Using linear least squares. The approach is this. Let's take this function f, approximate it around an initial guess, let's say theta naught, using Taylor series, and then from that estimate using linear least squares the next iteration theta, and use this as now a point in which to use in a new Taylor series expansion, and vice versa, and so on and so forth. So we're using this concept as a Gauss-Newton. It's called Gauss-Newton or nonlinear least squares, and this is called the Gauss-Newton iteration. Let's see how it looks like. So we can approximate y equals, and instead of f of theta, I will put the Taylor series expanded about a point theta naught, okay, about the initial point theta naught, plus the Jacobian matrix times a vector of theta, let's call it hat minus theta naught. Everything is our vectors here. So this guy I can call theta tilde, and this guy I can move to the left hand side and call this y minus f of theta 0. I can call it y tilde. So we have y tilde equals j times theta plus a noise, and we know that the solution for that is, and let's call it now theta tilde 1, is j transpose j to the minus 1 j transpose y tilde. Okay, so we solved it, and this is the first iteration. So now we have another, maybe more accurate guess for theta, and we can use it to expand again and to calculate the Jacobian matrix again, and to invert, pseudo invert this Jacobian matrix and solve for theta 2, and then for theta 3, and so on until it converges to a tolerance of error that we define. Now this is a fast converging solution. It's faster than the gradient descent, which we all use in machine learning and deep learning, but sometimes it's unstable, so we have to regularize the inverse here. It's called Tikhonov regularization, or two people that produce this method are called Levenberg and Marquardt, and it's called, this Gauss-Newton extended with regularization is called Levenberg-Marquardt algorithm. If you want me to deep dive into it with examples from industry, let me know, and I can schedule a lecture and invite you all. Thank you very much for your time. Appreciate it. Bye-bye.